Hello, good morning. Am I audible?
Yes, sir.
Good morning and welcome to our lecture on advanced power electronics. Yesterday we discussed zero voltage switching, and this zero voltage switching we applied to a DC to DC buck converter, and we find out a drawback of this particular zero voltage switching is that voltage rating of the device will be a more. So we require voltage rating, voltage appearing across this capacitor may be a 2 times of the VD, and so the device rating will be higher. And this problem can be eliminated with another resonant switch converter that will be ZVS CV, zero voltage switching clamped voltage. So here for that case we require one additional switch, and with the help of that we can both switches will turn on and turn off at zero voltage, so losses in the device will be less, and at the same time we clamp the voltage across the device will be equal to VD. So that thing we have studied yesterday. Today we'll go for a single phase DC to AC. We go for the inverter. So this is our single phase zero voltage switching clamped voltage DC to AC inverter. We are having a single phase inverter, and this configuration, if you see it, it is a half bridge or full bridge inverter. If you look at the configuration, we have seen that this will be a half bridge inverter. Okay, basically this will be half bridge inverter. We are having a induction motor load, and we are operating in the square wave mode. Very important thing is we are operating in the square wave mode. So our switching frequency is the 50 hertz. Switching frequency of the devices is the 50 hertz. And now here we have shown it here upper waveform. If you see the voltage, output voltage, this is almost a square waveform, but transition we are taking from negative voltage to a positive voltage, a very short duration. Similarly, from positive voltage to a negative voltage, we say this will be approximately the square wave. Our inverter is a square wave, so we are getting a single phase square wave output, and our load is a RL load, so definitely this will be our current wave shape. Okay, current will not be the sinusoid one because our input is the square waveform, and current we are whatever the wave shape we have shown depending upon the uh, inductance of the circuit and the back EMF of the motor. Based on that, we are having this will be a current waveform. So here we are operating at the 50 hertz square wave mode, and now our both switches will be turned on at zero voltage, and voltage is clamped because of the topology itself. Now let us consider regarding the output voltage. So let us consider a steady state case. Is it so? You assume, so we consider a steady state case here. Whenever our output voltage is positive here, let us consider this part of the waveform where our output voltage is the positive voltage and our current is positive. Output voltage is positive and current is positive. Consider the first case, our output voltage is positive and the current is also positive. Then which device has to conduct this? So our output is positive and the positive direction of current is left to right. This is our direction of current. So direction of current, we have shown it here. This will be a positive direction of current. And we are assuming the waveform here, steady case. Consider the case when output voltage is positive and current is positive. Positive direction of current is there. And so here it is obvious that our T plus device has to conduct. So we can say it here, this will be a T plus device will conduct like this. Okay. And we will get the output voltage is the positive voltage and our current is the a positive current. Is it clear? Is it clear? So whenever we are having both output voltage is positive and current is positive, output voltage is positive and current is positive, then our device, we have to upper T plus device has to conduct, so that okay, motor point will be connected to a our plus Vd by 2 voltage will be appearing across the input of the output voltage at positive output voltage. Now consider the case, now voltage is positive but our current is negative. So we'll make the current negative. So here current is negative means this is the direction of negative current. Let us assume that this is our blue direction. What we can call it will be a negative. But I want a positive voltage. I want a positive voltage. So which device has to be conducted? So here if you see it, current has the reverse current will not flow through switch. And the option available in that case is a D plus has to conduct. Okay, this has to conduct. So whenever we require a positive output voltage and negative current, positive output voltage and the negative current, then we have to device on will be a T plus, sorry D plus, device on will be upper, this device will be on. Let us consider, so here we consider this case, okay, where our current is negative and output is positive, where our D plus has to conduct. Now let us consider again steady state, voltage is negative and current is negative. Let us take the case negative current is our blue, and now our interest is current is negative and voltage is negative, both things are negative. So voltage is negative and current is negative, so this will be our negative current. I will mark it here, and the path, so it will be from this negative current, it has to flow through this T minus, okay, a negative current. So we are showing it here a negative current, then it will be a going. So this will be a negative current. Sorry, we'll make it here. So this will be our negative current. It goes to the battery, and from battery, it will go to the this like this, and from this is the negative direction of current. I will repeat once again. Consider the case. Consider the case when voltage is negative and current is negative. So voltage is negative means this has to be come in this. Our current is negative. So this is our negative current. Blue direction is the negative current. So I am tracing this. Our current is negative. So current will come from this. It will be through this motor winding. Through this it will come to the T minus, and from T minus it will go to this. So here we can say that whenever we are having both voltage is negative and current is negative, it has to be a T minus has to be conducted. Now our voltage is negative but current is positive. Voltage is negative but current is positive. In that case, we have seen that particularly our D minus, particularly D minus has to conduct. A D minus has to be conduct. Current is positive. So let us take current is positive. So here this will be our voltage, but current is positive. It will come to this. Okay, I have to mark it red. So we'll take it here. Red. So this will be the case. We have shown it here. This will be the case whenever this, and then it is so negative voltage and the positive current, a D minus has to conduct. So is it clear which devices has to be conducted for under steady conditions? When voltage is positive, current is positive, our device T plus has to conduct. Looking at when positive voltage and negative current, D plus has to conduct. negative voltage, negative current T minus has to conduct. Negative voltage and positive current D minus has to conduct. Any question on this?
No, sir.
Okay, now what will happen? We are not discussed this period. Is it right? We are not discussed the period where what is happening here whenever just our T plus here, let us assume that here this is the instant where our T plus is turned off. Positive, that T plus upper device is turned off. Then what will happen? Our current will be a positive. What will happen under this condition? We are considering this case here. At this instant, we are considering we have turned off the T plus. We have this device we have turned off. This T plus device we have turned off. But because of circuit inductance, we are having current is the positive. Current is the positive. Whatever our direction of current we have shown, the red current. And now our device is turned off. Device is turned off. And now this current, we are having two paths. This current, we are having two paths. One is whatever this current will find, I will just trace it from this red. If you just trace it to the motor winding, to the motor, this back EMF, then it goes to the center point of the DC. From this, it will charge the capacitor. So here C plus capacitor, whenever this switch T plus is on, when switch T plus was on, what is voltage across the C plus? When the T plus was on, we have seen that T plus and C plus, they are in parallel. And when T plus is on, voltage across C plus is 0. Voltage across C plus is 0. And we have shown one part that current in our motor winding is a positive current because of stored energy. And this current, positive current, we have marked with a red. And this path will be from motor winding to the DC center, tap of the DC here, from the VDC by 2 to this, and it will charge the capacitor. So red current, we can see that it will charge the plus current, C plus capacitor. Similarly, we are having another path, same positive current through it. Now you see that whenever this was off, earlier this voltage across C plus was positive. And now so C minus was positive. Voltage at this will be a positive during that instant. So this capacitor will discharge through the motor winding. This will be a blue color motor winding to the center point of this, to through this battery, it will come back. So here, whenever our T plus is turned off from steady state condition, and whatever energy stored in the inductor of this, it has having a two paths. One is marked with red color, and because of that, our capacitor C plus will charge it with upper polarity positive and lower polarity negative. So this will be a charging of upper capacitor C plus will take place. At the same time, whenever switch was off, the capacitor, the C minus is having a charge with this polarity earlier. And now under this condition, we have seen that a blue color indicates that this capacitor will discharge, give energy to the motor as well as to the DC supply. And whenever the capacitor fully discharges, whenever this capacitor is fully discharged, this capacitor is fully charged. Under this condition, now if the energy stored in the inductor is remaining, then we are having a third path, and this third path is shown with a green color. Now we are having third path which is shown with a green color. So from this positive current, you just trace from the motor winding to the center of this to the DC supply, and from that it will be a D minus. It will be a D minus. It will conduct and it will pass through this. So this is a transition where we have seen it here when our voltage is changing from negative to positive to negative. During that period, we have seen that current will pass through the C plus C minus. And whenever voltage becomes, our current is positive but voltage is negative, upper capacitor is fully charged, then we are having a path for the D minus. So similar will be the case whenever we are changing from negative to the positive. So we have marked here how the devices are conducting, that we have discussed just now. Is it clear? Any question on this? For each case, we have considered which device will be a conducting. Basically, we have shown the it is a lagging load. So our waveform, input voltage waveform to the motor is almost a square wave, whereas our current will be a wave shape. We have shown it here, and we have shown basically it is a our current is lagging the voltage by an angle. Some angle it will be lagging this. And here you see it here we mark the device conduction, and now if you see it here, so first D minus is conducting, and then we turn on the T minus. Here D minus is conducting first. This is the instant where we mark as D minus is conducting, and then our T plus is conducting after that. So D minus is conducting, so voltage across the device is 0. So when D minus is conducting, then we apply the T minus, so that our T minus is turned on at 0 voltage. Similarly, regarding the T plus, before that D plus is working, so that we are having this. So D plus is conducting, and after that T plus is conducting. So first diode will conduct, and then device will conduct. So that turn on is at 0 volt. During turn off, when the device is turned on, voltage across its capacitor is 0. So when we turn it off, the voltage across that device will be 0. So turn off will be at 0 voltage because of a capacitor connected parallel to the device. Because of capacitor connected parallel to the device, our turn off of device is at 0 voltage. And our turn on of the device is at 0 voltage because before turn on of that, the anti-parallel diode was conducting. And that's why we have shown it here. Our both devices will be a particularly turn on and turn off at 0 voltage. So any question on this?
No, sir.
Okay, now let us go for this can be controlled, okay, with the help of a hysteresis current control. So our sinusoidal current, it is a low frequency particularly, and then if you want to have a hysteresis control, so our hysteresis band should be the very large here. So this will be our average, and this will be a lower band. Okay, what I am tracing, that will be a lower band, and this will be a upper band. Okay, hysteresis already we have studied here. This is upper and lower, and we have shown it here. Our current is having a large ripple. If you want to control with the hysteresis current control, you want to current control, then definitely our ripple will be higher. For increasing the current, if you see it here, our current reaches, if you take this instant, our current will be reaching to a lower limit. We have to increase the current, so upper switch has to be turned on. So here we turn on the upper switch. At reaching here, we have seen that we want to decrease, so we turn on the lower switch. So that will be, so here we have seen that our uh, large ripple in the output current. That will be a drawback of this single phase ZVS CV DC to AC inverter. So we just okay, we'll just here summarize. We have discussed the half bridge inverter, anti-parallel diode, and capacitor is connected, and we have seen the role of diode, capacitor during the operation. And particularly for this ZVS CV, we see that our load should be a lagging power factor, and that will be a normal case. We are having turn on and turn off of the voltage at 0 voltage. We have discussed. Anti-parallel diode is conducting before switch is turned on, so that 0 voltage turn on is possible, because anti-parallel diode is conducting voltage across the switch, and diode will be 0, and then we are turning on the switch, so that the device will turn on at 0 voltage on. Turn off at 0 voltage because across the switch we are having the capacitor, and when the switch is closed, the voltage across the capacitor is 0. When you open, again the voltage across the switch will not across the capacitor will not increase to a higher value, and definitely our turn off will be at the 0 volt. So this is all about our 0 voltage switching. We have discussed this will be a for a half bridge inverter, single phase inverter, half bridge single phase inverter. Same can be extended to a three phase bridge inverter. So here already we are having IGBT devices with anti-parallel diode. That is the inherent feature of our inverter VSI. And in that case, addition is you have to just put the capacitor here. Okay. And operation is on the similar lines what we have just discussed for the single phase. So before turning on this, anti-parallel diode is conducting, so turn on will be at 0 voltage. And when the switch is off, we have seen that capacitor is there and it will be at the 0 voltage. So turn on will be at the 0 voltage. So here we can use a three-phase ZVS CV DC to AC inverter, a conventional BSI, but we have to put a additional capacitor across each device. That will be the required. But one drawback is that particularly we are having a very large ripple in the output current. Okay, and now let us, so this will be our second topology, that is the resonant switch converters we have completed. So any question on resonant switch converter?
No,
Any
sir.
question?
No.
Now let us discuss the last topology in the resonant converters, and that is a resonant DC link inverter. So inverter, whatever input DC voltage we are giving, that we can call as a DC link. And our DC link voltage is, in case of VSI, our output voltage in case of DC. So let us assume that this will be a 0 volt. Already we are having it here. So this is a DC link voltage waveform I am showing. A conventional case, in case of VSI, our DC link voltage will be a, this is our, let us assume that, and this is our DC voltage. DC link voltage is a constant and ripple free. This is a DC link voltage is a constant and ripple free. We'll show it here on the diagram. This is our DC link voltage. So this is our DC link voltage in case of VSI, a constant value. This is 0 volt here, this is value. But whenever we want to make the link to resonate, then we have seen that a particularly DC link voltage is not remaining constant here. How is it in case of a voltage source inverter? But it will be resonating the like this, whatever we have shown it here. It is a high frequency making 0 and double the VD. But average voltage will be a V, whatever we are having. So this will magnitude will be a twice V. Okay, we can call it as a twice V as our, this is our V. So in case of conventional VSI, in case of conventional VSI, this is our DC link voltage will be a constant and a ripple free. But in case of resonant, the same our DC link voltage will be become a twice V, and it is oscillating DC. It is going to a 2 times of V coming 0 and this. But the average, if you find out, average voltage of this waveform is the same as VDC. So that is the difference between DC link voltage in case of VSI. This is the DC link voltage in case of our conventional voltage source inverter. We have discussed a 2 level, 3 level, 5 level, whatever multi-level inverters. In that case, the VSI voltage source inverters, we are having DC link voltage is the constant. But in case of resonant DC link, we have seen that our link voltage is oscillating and it goes to the 2 times of the average voltage. So our DC link voltage is the oscillating from 0 to 2 times of this. And our inverter, okay, inverter, we can turn it on and turn it off. Inverter switches, whatever we are having the switches in the inverter. So whatever the switches in the inverter we are having, these switches we have to turn it on or turn it off, particularly when DC link voltage is 0. And we have to get this from fixed DC. We want to have a resonating, and particularly we required a LC resonant circuit will be introduced between the supply and the PWM inverter. So here, so this is our DC voltage. If you see it here, this will be a DC voltage. This is the L and C, the required components for resonating the DC link voltage. This is the L is L and this is the RL. Okay, we neglect RL for the case a small inductance, small resistance of the inductance circuit we are having, or it is a practical inductance where inductor has a winding and that winding resistance of the inductor is represented as RL. So we are having a LR and the CR for the resonating components. We require one switch across this. So, okay, if you are a LC, then we are not having any disturbance. We cannot create uh, oscillations, and for that we require one switch. That is T will represent as a one switch. And now this is our conventional voltage source inverter, VSI, uh, or the three-phase bridge inverter, conventional bridge inverter. We are having this. And now our current, DC link current is almost constant. Okay, whenever we are operating this with a particularly any PWM technique, then definitely this DC current will be almost constant for a particular load condition. So for simple representation, so this bridge inverter with load can be just represented as a current source. So bridge inverter with load, we can represent it as a current source. So now we can see this will be our very simple equivalent circuit. So this will be equivalent circuit where this whole this inverter and load that we represented as just as the current source. We represented just as the this whole we can represent it as the current source, and other components are as it is. Other components are as it is. So here we are required the, so in brief we can say that we are required the LR and CR. We require the LR and CR so that we can make the DC link to oscillate. With the help of LR and CR, we make the DC link to oscillate from 0 to 2 times. If it is a VD voltage is there, our voltage across this DC link may go up to 2 times of VD, or sometimes it may be a 3 or 3.5 times of the DC is also possible, depending upon the amplitude can be a controllable one. So is it clear now how the we oscillate the DC link, how the oscillations in the DC link can be made? Any question up till now?
No, sir.
Now let us our interest is how to create the oscillations in the DC link. Okay, how to create the oscillations in the DC link. And for creating the oscillations in the DC link, we are providing one switch. This is the switch we want to provide. Whatever this waveform we have shown, it will be under a steady state waveform. We are having a steady state inverter is working with some PWM technique. We are going to discuss the PWM technique for this particular inverter is different, and particularly we are calling as a sigma delta modulation. We are not using the sinusoidal PWM in this case. We are using the sigma delta modulation technique that we are going to this, and this is our, so under steady state this is carrying a current I0. So our inverter input current, our inverter input current, if you see this will be a inverter input current. What we are having is a inverter input current I0, that will be a constant and ripple free. Whatever I have shown with red, that will be this. Whereas we want to resonate this, in that case our IL will not be a, it will be DC. IL current will be DC, but it is varying within the two limits. So our IL current, particularly our IL current is not the constant. IL current is not the constant like I0, but it is having because of the we are considering steady state, and this will be our I0. IL, sorry. So this will be IL, and this IL we have seen that average maybe comes out to be the same. Okay, whatever I0 and the average of IL will be the same. But IL will have a higher, sometimes higher value than the IGO, sometimes lower value than the IGO. Now let us consider here. Okay, we close the switch. This whatever this T switch, we close at T0. We close at T0. Okay, whenever we close the switch, what will happen to a DC link voltage? DC link voltage is nothing but this. Okay, this points A, B, you can call it. This is the A point, and this is the B point, where we connect the inverter input to the inverter. Okay, we are DC, we are applying it here, and when we connect this, we can say that we are shorted the DC link. Is it right? We are shorted the DC link. So DC link voltage will be 0. We are coming it here. We are 0. And whenever our current is 0, and now we have seen that I0 is remaining same, but our because of shorting, our IL will increase because of the shorting of this particularly switch or turning on of the switch. Turning on of the switch, we have seen that our IL will be definitely greater than I0. IL will be greater than I0 because some current will be flowing through the switch. I0 is as it is, but some additional current will flow through the switch, and because of that our IL will increase. Okay, so as IL will increase, now a very short duration after that. So this switch is only very short duration we can make it on. Okay, few milliseconds or you can few microseconds you can call it. So this switch is we are just making it on for very short duration, and after the switch is shorted, then we open it, and during that period inductor will store the energy because large current will flow, increase of current. So the because of the energy stored in inductor, now our current IL will go on increasing, then go on decreasing. So our capacitor voltage will now reach, okay, capacitor voltage. Now the current, this extra current will be flowing through the capacitor. The path for this I0 is fixed. Now this IL is more, so this extra current will flow through the capacitor. This extra current will flow through the capacitor, and because of that, our capacitor voltage will goes on increasing. And whenever our inductor current will become equal to the same, our capacitor voltage is a twice with the polarity of this. Okay, upper this and this. And now then what happens? Now this again our LC circuit, then this current will again reverse its direction. Earlier it was flowing like this, whenever then now it will be flowing in this like this direction. And because of that, now our current, IL current will be this. So total we are getting this current, and whenever the now capacitor will, we can say it will be a capacitor voltage is decreasing, and again capacitor voltage will become to a 0. And now again here, whenever capacitor voltage comes 0, again we can close this switch, and as again we close the switch, again our this IL has to greater than IO. So IL should be a greater than IO. So in this fashion, we can just resonate the DC link. So whenever voltage across, let us assume under steady state, whenever voltage across capacitor becomes 0, at the time this capacitor we can short, and whenever we can keep it very some short duration, so that current through the inductor will increase more than its I0, and after that we turn off the switch because of stored, then our current will increase. As current increases, the voltage across capacitor will increase, and when this increased current becomes 0, capacitor voltage will reach to a maximum value, and after that again our current will reverse in this, and capacitor voltage will decrease. So this will be a voltage across CR oscillates continuously. This is a very short duration we have expanded, and we have shown that how our voltage across the capacitor will be oscillating 2 times of the VD. Okay, this is the one we have discussed. So any question? How we resonate the DC link, and for that resonator we have to generate these oscillations. We have to short the DC link for very short duration. Okay, and now this particular job. Now here we have shown that when this voltage is zero, we keep the switch on here so that a particularly current will be become this IL current will be become more than the I0. Okay, more than the I0, and so that the oscillations will continue. So and this we have to maintain it on, because of we are having some losses because of this component. We are having some losses in this circuit. So is it clear how we create a create the oscillations in the DC link? And now this switch, okay, this switch we can replace. Now this switch is instead of one leg of the inverter itself can do the job. So this is our practical uh, a resonant DC link inverter. So this is our practical resonant DC link inverter. This is the LR and the CR. This is the LR and CR required for creating the resonance in the DC link. And we can use any one leg, two devices in the same leg we can turn on, because we don't require an additional switch here. Whatever switch present in the particularly inverter we can use for, so S1 S4 we can turn on, or S3 S6 or S5 S2, any one leg you can turn it on, so that we can turn it on for very short duration, so that the current through will increase it, then make it open, so that we get the oscillations of the voltage across the capacitor. And now we have seen that how the oscillation waveform. Now we have shown the oscillation waveform across this capacitor is this. It will be having a 2 times of V. It is going 0 to 2 times of the V. And it is oscillating with some particular frequency. And we have seen that whatever turn on and turn off of these switches. So we have to make any PWM technique where we have to turn on some switches, turn off some switches, so that we will get the AC output. Is it right? We have to turn on and turn off the switches. So simultaneously, how many switches will be conducting? In our case, 180 degrees mode, three devices will be conducting, one from each leg. At one instant, we have to switch off one device and turn on another device. And that whatever turn on and turn off device, and that instant is when our voltage across the capacitor is zero. When your voltage across capacitor is zero, we can turn on and turn off the switch, so that we can get the required AC output voltage. So switches can be turned on and off at zero voltage, when the DC link voltage will be a zero. So any question?
No, sir.
Okay, so here, so any leg, okay, both devices. Now in case of VSI, it is not allowed to turn on the S1 and S4 simultaneous. It will short the DC link. But whenever we are having an inductor and we require this particular to resonate the DC link, our two switches in the one leg for very short duration we can turn on, so that we can maintain the oscillations in the DC link. Our interest is this DC link voltage may go 2 times or may go up to 3.5 times. But to have a voltage rating of device, now normal practice is this voltage across the capacitor is not allowed more than 1.5 times. Here we have shown it is going to a 2 times. Okay, it is going from 2 times, but it is advisable not going for a 2 times. We can clamp it to a 1.5 times. Okay, we can clamp it to a 1.5 times. And for that, we are using one additional circuit, that is a voltage clamp, active voltage clamping. We are using one additional circuit that we can call as a active voltage clamping. We have done it. And what is the purpose? We have to limit the maximum value of voltage across the capacitor will be 1.5 times. If you not clamp it, it may go 2 times, or it may go around maybe a 3 times. And for that, voltage rating of devices will be more. And for that, so we are providing the uh, active voltage clamping to the DC link. And normal practice is we have to provide the this voltage may be 1.5 times of the voltage, not the two times. Whatever here we have shown, the this waveform we have shown it as how many, two times of this, but we have to limit you to a 1.5 times, so that the voltage rating of the switch can be reduced, and our clamp should be lossless. Whatever circuit we are using for clamping the DC link voltage, that should be lossless. No losses should be taking place. Is it clear why we are limiting the maximum DC link voltage to 1.5 times? Reason is we want to save on the voltage rating of the devices. Our voltage rating of devices should not increase, so that we limit our maximum voltage across the capacitor. During that resonance, it will be kept at a 1.5 times of the DC link voltage. And now here we are showing you the circuit, one additional circuit we are putting across the inductor. We are putting across the inductor to limit or clamp the capacitor voltage, 1.5 times, 1.5 times of the DC link voltage. So what are components we are using across the inductance LR? So here we put one additional switch here, IGBT anti-parallel diode, that switch, and one pre-charge capacitor. Here voltage across capacitor, if we can write it here. Voltage across the capacitor K minus 1, okay, K minus 1 into input VD. Voltage is we represented as the input as the VD. Our input is VD. So here we want to maintain maximum voltage is 1.5 times of VD. So K will be, this capacitor voltage will be a 1.5 minus 1, so 0.5 VD. So this will be a normal DC link voltage. So this is a normal DC link voltage. It is a VD. Then how much will be we can pre-charge the capacitor with how much voltage? The voltage across the capacitor is K minus 1 into VD, and our normal K will be 1.5. So we have to, our voltage across the capacitor should be 50% of VD. We can call it here. So whatever this capacitor we are putting, C capacitor, and voltage across that capacitor will be equal to 0.5 VD. So voltage across the capacitor, whatever the voltage across this capacitor, particularly this capacitor, we can call as VC, you can call it this. VC will be equal to how much? A 0.5 VD. A 0.5 VD. We'll add together. So this is the upper terminal is positive, lower terminal is negative. So this is negative, upper terminal is positive. So that will be a charge on the capacitor. Whatever we additional capacitor we are using, that voltage should be equal to a 0.5 VD. Okay, and polarities will be shown. So this is a VD plus 0.5 VD. So it is a 1.5 VD. Okay, it will be a 1.5 VD. Now, particularly, where resonating frequency may be given 5 kilohertz or the or 10 kilohertz. Now, how the circuit works, is it right? So, whatever we are putting additional circuit. So, what is additional circuit? A capacitor and switch we put across a resonating inductor. And what is the purpose of this circuit? This our purpose of this circuit is our capacitor voltage should not increase to twice VD. We want to limit it to a 1.5 VD. We want to limit it to a 1.5 VD with the help of this capacitor and this particular switch. So any question? What is purpose of active clamping?
No, sir.
What is the purpose of active clamping? Anybody?
So it is for protection, sir.
So, so only 21 people are attending class at present. CR.
Sir, I told them to attend, but
Okay, okay, that is all right. Okay, I don't have, okay, no objection for that. But I am just saying that only 21 people are attending the class. What is the intention? I don't understand what is the intention for this case, particular case. I will not give the link and anything else onward. Okay, let us forget the things. Okay, that will be okay. We can think of that. Is it right? Okay, if you are giving a undue benefit of the situation, so it is not necessary. Why we should be? Okay, you are not urged to learn. You are not asking questions. Your active participation is not there. Then what is the use of doing this whole exercise? Just out of 74, only 20% people are attending, or 25% people are attending the class. What is intention? I will not provide the PPTs and the link. Okay, so will not. Okay, let us forget the things. You have to prepare yourself. You are so confident that I don't bother about that. Okay, so henceforth I will not provide any PPT, any any PPT, and the link of the lecture is not provided to you. So you say all the other people that henceforth you will not be allowed to do this. Okay, I am not providing anything. You have to listen the lectures or let us forget. So now what we are discussing was about the. So is it the screen is visible?
yes, yes, sir.
Yes, sir.
So so this will be what we are having is particularly. Hello, CR.
Yes, sir.
Hello. Yeah.
Yes, sir.
We are making one practice. You have to, those people who are attending, you can send me a snapshot.
Okay,
Whenever
okay.
background people are appearing or whenever you want, okay, you can send me that so that I can keep the attendance record. Okay, okay, that is it possible? After the lecture, you can see that, okay, put in that mode, and those who are present, their snapshot, can you send me?
Okay, sir. I will try.
You follow this practice from this lecture onward. Okay. So today you can give me just okay snapshot those who are 21 or 22 present. Okay. So that we can see. So we were discussing about this the resonant DC link inverter, and we are going for why active voltage clamping is required. So what is the purpose? Why active voltage clamping is required? Why we require active voltage clamping?
For protection.
Once again,
Protection.
active voltage clamping we required so that our DC link voltage should not exceed more than
More
1.5.
than.
Why it should not exceed 1.5? If it is exceed 2, what will happen? Instead of 1.5, if this voltage across the capacitor exceeds the 2 times of the VD, then what will happen? Our device ratings, the same voltage will appear across the device. So our device rating, device voltage rating will increase. Means we have to use the devices of higher voltage rating. And when we are using the devices with higher voltage rating, the cost of device will increase. Okay, the main reason why we are going for active voltage clamping is to reduce the voltage rating of the device. We want to reduce the voltage rating of the device, and that is the reason, okay, for that we are using the active voltage clamping. And which components we are using? We use one capacitor, and voltage across that capacitor will be just the 50% of DC supply. Here DC supply is 600, then how much voltage across capacitor? 50% of that, that will be 300. And we use the this particular switch, and with the help of that it is possible to maintain the DC link voltage, limit the DC link voltage, or clamp the DC link voltage to 1.5 times of its DC input. Now how this circuit works, how this circuit works, I am just taken as a one leg, the same part of circuit. Okay, this part of the circuit I am just taken it here for discussion how this circuit works. Okay, if you have shown it here, a red path of current. Okay, a red path of current. If you see it, that current will pass through the switches Q1 and Q4. What is purpose of this turning on Q1 and Q4? What is the purpose for turning on Q1 and Q4? Why we have to turn on Q1 and Q4?
Charge the oscillation.
Okay, we want to start the oscillation. That Q1 and Q4 will doing the job of this switch. Q1 and Q4 will doing the job of this switch. We want to start the oscillations. So for start of oscillations, we have turned on the Q1 and Q4. And when Q1 and Q4 are turned on, when Q1 and Q4 are turned on, voltage across capacitor will become zero. Voltage across the capacitor will become zero. Okay, that is one thing. And because of this, voltage will be appearing across the inductor. Complete VD will appear across the inductor because this point will be coming it here. So inductor will come across this. Inductor will come across the VD, and because of that inductor current will try to increase. It will increase at a particular higher rate. And this okay, this Q1 and Q4 we are just turning on for very short duration. Q1 and Q4 we are just turning on for a very short duration, and after that we both will be turned off. And now because inductor current will be increasing, so whatever we just discussed this, as our inductor current will increase. Okay, and because of that the capacitor voltage will increase. Inductor current, okay, that additional current will flow through the capacitor and the capacitor voltage will increase. But whenever this capacitor voltage will increase to 1.5 times of this VD, because this point, if you see it here, I will just mark this point. This is the point. Okay, here if you see the upper point here, if you mark this point, this voltage will be 1.5 because this is a VD and this is a 1/2 VD, so it is 1 point VD. And whenever capacitor voltage will be a greater than 1.5 VD, when the capacitor voltage is a greater than 1.5 VD, what will happen to the diode? What will happen to the diode? When capacitor voltage, here a cathode of the diode is at, if you take this as a reference point, if you take this as the reference point, with that a point here, this point is at 1.5 VD. Okay, cathode of the diode is at 1.5 VD with reference to this point. And when capacitor voltage will be more than 1.5 VD, obvious reason is that our diode will forward bias. Our diode will be a forward bias. So here we have seen that when the diode is forward bias, the current will flow like this. Current will flow like this. Is it right? This will be the current. It will be a flowing, and it will shown with a blue color. So whenever our link voltage, the voltage across capacitor exceeds 1.5 VD, diode will forward bias, and this inductor current will flow through this. And inductor current has a opposition. And now here, whenever if you see it here, whenever we just turn on the Q1 and Q4, if you turn on the Q1 and Q4, current will increase. And whenever current will increase, that increase of current will be opposed by the polarity of inductor voltage. So whenever this red current is flowing, just when we turn on the switches Q1 and Q4, that time uh, left and right, you have seen the polarity across the inductor is like this will be positive and negative with the red. But whenever voltage exceeds above 1.5, this diode conducts, these devices are off now. And whenever this diode, now we see that our rate here, if you mark the rate of current, here rate of current is increasing. Is it right? I'll just mark that this is the rate of current is increasing. Okay, here whenever we close the switches Q1 and of rise of inductor current is the increasing, and for that we are having this the voltage polarity across the inductor. And here whenever our diode starts conducting it, opposition is there, and because of that our rate of rise will be decreased. So for particularly whenever for a blue color, for a blue color, we have seen that our rate of rise will be a decreasing one, and inductor will provide a polarity such as that this portion, if you see it here, the polarity, right side will become positive and left side will become negative. And if you try to force the current through this, okay, and it is as a maintained. So here, and whenever this diode conducts, after that we turn on the Q. After that we turn on the Q. When the current will become zero, then whatever slight stored energy in the inductor, that will prevail through the Q and balance the capacitor voltage and balance the capacitor. So this is how the circuit operation will take place, and that we have just listed it here. So we are putting a pre-charge capacitor. We are putting a pre-charge capacitor in series IGBT diode pair. When DC bus is short is released, link voltage shift towards the natural peak. When the voltage level reaches 1.5 VD, diode conducts and clamp the bus voltage to 1.5 VD. And when diode conducts, at the same time we turn on the Q. So here diode conducts, when we turn on the Q, when diode conducts, again turn on of this switch will be at 0 voltage to reduce this. And trapped inductor current will decay to 0 and then becomes negative, and this negative current will flow through the Q to balance the capacitor voltage. Okay, and whenever current through the switch becomes 0, Q will be turned off at 0 current. So this is the working how this circuit works. Any question on this? How this circuit works? How the active voltage clamping works? Okay, and now let us go for what will be disadvantage of this circuit. So advantage we have seen, our device voltage rating will be a small. Disadvantage will be it needs extra components and additional loss in the resonance circuit. Okay, that will be the drawback. We require one capacitor additional, one switch additional is required, and a loss in that particular devices. So now we stop here. So whatever the one technique how to control this, we'll discuss tomorrow. Any question? Hello?
No, no, sir.
Okay. Sorry for I think late by 2 minutes. Okay, so okay, we'll meet tomorrow at the same time. Thank you.